Good morning, everyone. Today I'll be talking about priority based scheduling algorithms, an important concept in operating system that helps manage how different processes are executed by the CPU. We'll explore what it is, how it works, its type, and where it's used in real world systems. CPU scheduling, the foundation. To start off, let's understand what CPU scheduling means. CPU scheduling decides which process should uh, run at a given time on the processor. The goal of the scheduler is to make smart decisions that improve performance, like maximizing CPU usage, reducing waiting time, and making sure all processes get a fair chance to run. In modern operating systems, CPU scheduling is critical because multiple programs compete for CPU time simultaneously, like browsers, downloads, background, updates, and more. Now let's understand the core objectives of scheduling. The main objective of CPU scheduling are to maximize CPU utilization, meaning we want the processor busy most of the time, to minimize waiting time for processes in the queue, to optimize turnaround time or the total time from processes start to completion, to ensure fairness so no processes get ignored for too long, and to maintain responsiveness, which is especially important for interactive systems like phones and computers. Priority based scheduling overview. Now let's focus on priority based scheduling itself. In this method, every process is assigned with a priority number. The CPU is always given to the process with the highest priority, meaning the one that's considered most important. This approach is great for systems that need to handle critical or time sensitive tasks first, for example, real time systems or operating system tasks. Lower numbers usually mean higher priority, and priorities can even be adjusted dynamically while the system's running. Preemptive versus non-primitive uh, priority scheduling. Primitive priority scheduling. If a high priority process arrives while another is running, the CPU immediately switches to the new one. This is used in real-time systems where quick responses are needed. And non-preemptive priority scheduling. Once a process starts, it runs until it finishes, even if a higher priority process arrives later. This is used in batch systems where minimizing context switching is more important than speed. Algorithm execution step by step. Here how the algorithm works step by step. Processes arrive and enter the ready queue with assigned priorities. The scheduler sorts the queue based on priority values, and the highest priority process gets the CPU. Once the process finishes or yields, the next process is chosen, and in preemptive mode, if a new process with higher priority arrives, it immediately interrupts the current one, and in non-primitive mode, the running process is completes first before any change. Gantt chart example. Let's look at an example to understand better. We have five processes P1 to P5, each with arrival times, burst times, and priority values. Priority 1 is the highest. In the primitive version, the execution order becomes P1, then P2, then P1, then P4, then again P1, then P5, then P3. From this, the average waiting time is about 6.4 units and the average turnaround time is 10.6 units. This example shows how high priority process gets the CPU earlier, improving responsiveness for critical tasks. Now let's talk about the advantages and limitations. Advantages is that critical task priority ensures urgent processes are handled first. Flexible control, priorities can be changed dynamically. Optimized performance, different workloads can be balanced effectively. Limitation, starvation risk. Low priority processes might never get CPU time, and it can be hard to assign correct priorities. Frequent switching in primitive modes increases CPU overhead, and to stall starvation, systems often use aging, which gradually increases the priority of waiting processes so that they eventually get CPU time. Now let's compare priority scheduling with other algorithms. In priority algorithm, the preemption is option, starvation is possible, overhead is medium high, and it is used in real-time systems. While in FCFS, there is no preemption, no starvation, and very low overhead, and it is used in batch jobs. In round robin, there is preemptional, there is no starvation, high overhead, and it is used in time sharing systems. Priority scheduling offers the most flexible priority scheduling offers the most flexibility, especially when process importance varies, but it must be implemented carefully to avoid issues like starvation. Real world applications. Priority scheduling is widely used in real systems. In operating systems in like Windows and Linux, it's used for kernel threads and device drivers that need instant response. In real-time systems like industrial controls, safety sensors get top priority over non-critical tasks. And in network routing, quality of service gives higher priority to voice or video packets compared to background data like file downloads. To summarize, priority scheduling helps manage critical tasks efficiently by assigning important levels. But to make it fair, mechanisms like aging are needed to prevent starvation. So priority scheduling is powerful, flexible, and widely used, but it must be designed carefully for the best balance between performance and fairness.